Good morning, everyone. Thanks for coming to this session. This session is about information modeling techniques, and there will be 7 presentations upcoming, and 2 of the presentations will be pre-recorded, but you will still have a chance for a Q&A session with the authors. My name is Junxiang Zhu. I'm a researcher from the University of Cambridge, but before that, I was a senior lecturer at Curtin University in Australia. This is my co-chair, Jun An, right? Jun An, yeah. And yeah, so this session will be recorded, and the recordings will be uploaded to a YouTube channel. And if you are not happy or have any concerns, please let me know, and your session will be removed from the YouTube channel, right? Okay. So each session will have 10 minutes. So each presentations will have 10 minutes for a talk, right? And 3 minutes for Q&A and 2 minutes for translation. Yeah, so we'll be very strict on the time. So please be aware of this. Okay, so it's about time, right? Yeah, right on time. So the first presentation is application of beam technology to soil layer risk analysis for enhanced accuracy and informed decision-making in geotechnical engineering by Wen-Yi Wang from National Kaohsiung University of Science and Technology. And the floor is yours. Yeah.
Hello everyone, my name is Wen-Yi Wang. I am from Department of Civil Engineering at NKST in Taiwan. Today I'd like to share my topic. Okay. Here is quickly outline of my presentation. This study is mainly to produce information-rich soil BI model for serving as a basis for returning structure design, construction method selection, and risky prediction. 2 advantages about this soil model. First one is introducing the concept of fragment soil modeling to enhance the realism of subsurface representation. Second one is enabling the identification of potential weak loam and localized high-risk areas. First, I'd like to introduce the system framework of this study. We use ISARC and Civil 3D software to combine on-site borehole data and surface elevation data to accurately capture terrain condition for DEM. Then we imported the data into the Dynamo to automatically generate soil model. And then using Excel for correction about soil layer federation. Finally, we imported the data into Dynamo to automatically generate the final soil BI model. This slide shows a workflow of soil modeling. The workflow divided into 5 steps. Step 1 is surface generation. We use ISARC to capture source data from BMS and GIS. It can automatically generate a source model with a elevation point, contour line, and thin surface. This model was exported to Civil 3D via IMS format, where terrain is represented as a tin. Then we create a 20 by 20 grid and interpolated the elevation at each point based on the tin, capturing detailed terrain information. Finally, the 400 points were exported as a TST field and for its use in Dynamo. Step 2 is 3D borehole current generation. This image shows a 3D borehole current generated from 2D drawing reporter. They include soil classification data. In the Dynamo, we convert this classification into a different points, and then visualize them as 3D borehole current, as color code 3D current to represent different soil types. Step 3 is soil layer model generation. We connect these points mentioned earlier to form geological layer. However, if the input data is uneven or incomplete, model error may occur, such as misaligned or distorted surface. To fix this, we plotted the problematic points to Excel, adjust them using nearby reference data, and then re-imported them into a Dynamo. This helps us generate a smaller and more accurate soil model. Therefore, is the generation of fragment soil blocks. After building the main soil model, we further identifying heterogeneous materials in the borehole. They are different from the main layer. These areas are treated as broken soil long, and we perform local modeling around them. Each abnormal point is planned to 11 times 11 local grade. And we use the main model to interpret the top and bottom boundaries. Then we generate a local surface mesh with using dynamic triangulation. Apply the correct material and embed them into the main model. Therefore, is soil property assignment to enable automatic soil risk assessment later on. Our soil model needs more than just visual accuracy. It also has to contain usable data. These two Dynamo nodes play a key role in this process. First one is division by geometry. Division by geometry node convert the soil model into a convert the soil model in Dynamo into a division element in Revit. Then element state parameter might then assign geotechnical values such as N values, water content, and liquid limit. To each soil layer element after created. For example, this image shown on the right side, the selected layer is salty clay soil. The N value is 6, water content is 23%, and liquid limit is 47.7. These values are stored digitally in the reference model, making them easy to access or use for further analysis. After building the main soil model, we integrated foundation engineering with the BIM technology with the goal of automatically identifying and visualizing soil risk underground soil risk during the design phase. Next, I will briefly introduce key risk factors for foundation safety. We use 3 key parameters from soil mechanics, N value, water content, and liquid limit. In this slide, we show how the system checks for soil-related risk. First, for diaphragm wall. For diaphragm wall or prepared pile in soft clay, if the N value is less than or equal to 4, water content is greater than or equal to liquid limit. The system detects a clay risk and shows with a bounding box. Next, for diaphragm wall in loose sand, if the N value is low, if the N value is less than or equal to 30, it flags a sand-related risk and mark it visually. Finally, for CO2 pile driving, the system checks if softer soil sits on the top of much harder layer. This softer over hard condition is risky because the vibration from pile driving can cause the softest layer to liquefy. To detect this, the system compare the correct layer N values with the overall average. If it is lower than the average, a liquefaction risk is displayed and shown with a bounding box. Next, I will briefly introduce the case study. This project is in Gusan, Kaohsiung in Taiwan. We drill 12 borehole, but the B9 was selected because it close road and building. This soil has more loading. It also has contain low N values, which indicate relatively softer soil. The B9 soil reporter is showing right figure. This one shows the analysis result of the project. As shown in the figure, the liquefaction risk from pile driving is mainly between 0 minus 1.5 meters to minus 9 meters. The mud inclusion or breakage risk for diaphragm wall and prepared pile appear between 0 minus 4.5 to minus 9 meters. The sand inclusion risk during diaphragm wall construction occur at deep layer from 0 minus 9 to minus 30 meters. These deep zones are critical areas that need special attention during construction. To warm up, here are the main conclusion of this study. First one is integrating BIM with the soil property and risk analysis to improve geotechnical design accuracy. Second one is help reduce construction risk and develop appropriate mitigation strategy. Third one is although the system currently perform automated risk identification, future work should continue to incorporate real-world case to enhance model validation and accuracy. That's the end of my presentation. Thank you all for listening.